functions of complex variables. So suppose z is equal to x plus iy. So z is a complex variable because it consists of x and y, which are variables, and they are combined like this, and so this is a complex variable. So we know complex variables. Now we move on to functions of complex variables. So if I have a function like this, w is a function of z, where z is a complex variable, we call it a function of complex variable, and we will find that w is equal to u plus iv, where what is u? U is a function of x and y, and v is also a function of x and y. Now let us look at this one, and let us look at an example. Let us try to see whether this can be done. So let us take a variable, complex variable, z is equal to x plus iy. So if we have a complex variable, z is equal to x plus iy, and then let us look at w, which is a function of z, and here let fz is suppose z square. So what will be, that means w, this is looking like omega, I'll write it as w. So w is equal to z square, means x plus iy whole square, which is equal to x squared plus 2ixy plus I squared y squared, which is equal to x squared minus y squared, because I squared is minus 1, plus I 2xy. So look at this and this. This is in the form u plus iv, and so what is u here? Where u is equal to x square minus y square, so it is a function of x and y. And what about v? V is twice xy, and it is another function of x and y. So obviously we see that w is equal to u plus iv, where u is a function of x and v is also a function of x, and that is what we saw here. We saw that yes, if z is like this, then w, a function of z, can be written as u plus iv, where u is a function of x and y, and v is also another function of x and y. So we took just one example, but there can be for all examples of functions, it may be any kind of function. So it can be broken up into two parts, u and v, which are separately two different functions of x and y. Now I hope I have convinced you. We can move to single valued functions. What are single valued functions? Single valued functions, multiple valued functions. So let us see what are these. So single valued, first let's look at single valued functions. Suppose, so we had obviously seen that w is equal to f of z. Suppose this is a function of the type z square, or twice z, or z square plus 1, whatever. So you see, when I put a value of z, I get a value of the function fz, that is w. I'll repeat again. For every value that I give to z results in a particular value of w, because you see when I put it here, this becomes 1 square plus 1, which is 2. I put here 2 instead of z. I give the value z is equal to 2. So what I get, z square is 4, 4 plus 1, 5. So I get a value of y. So this, when one value of the independent variable, which is z, gives like this, a dependent variable, we call it single valued function. But then there are certain functions which are not single valued, they are multiple valued functions. And students, this is not applicable only to complex variable. We have the concept of single valued and multiple valued functions in all kind of variables. So since this has come up in complex variable, I am mentioning this, but it's applicable everywhere in the field of functions of variables. So I have another w is equal to fz. See, I have a tendency of writing this as omega, but this is w. Suppose w is equal to z to the power half. Now look at this. When I put z is equal to 4, what do I get? W. I have two values. So I have plus minus root over 4, which is equal to plus 4 and minus 4. You see? So again I put another value, z is equal to 9. What I get? W is equal to plus 3 and minus 3. So it's not just 4 and 9. Even if I put some other number, z is equal to some other number, suppose 3, still you'll have two values. So we'll get square root of 3 like that, square root of 2, we'll get like this. So we'll always have 2 like this. So this type of functions where a particular value of the independent variable gives rise to different values of w are called multiple value functions. In this particular case, the multiplicity is 2. We have two valued functions. There may also be more than 2 actually. So we'll come across such kind of examples. This is multiple valued functions, and there are certain terms connected with multiple valued functions, that every multiple valued function can be considered as a collection of single valued functions. So each member of which is called a branch of the function. So you see, we have a two branches, plus 4, plus 3, and so on. Here we have minus 4, minus 3. So this is a branch and that is a branch. We call it branch, and we will know more about branches later on. Then comes the concept of inverse functions. Now what are inverse functions? Inverse functions are like this. It's just like this. See, we had z, we had w is equal to fz. So then what is z from here? Z is called like this, and this is called inverse function. So inverse function is like this because if I find w is equal to z square plus 1, obviously what is z? It is equal to w minus 1 the whole to the power half. Is it not? So can I not say it is a function? So if I write that w is equal to z square 1 plus 1, is equal to fz, so I can call the z is equal to f inverse of w is this function. So this is what is inverse function, and these things are not unknown to us. We are just relearning these things. Then there are different types of functions in Z, and those are called elementary functions. So let us look at the elementary functions. Elementary. See students, these are ideas that are in the Swarm series book by M.R. Spiegel, Complex Variables, that I showed you in my last class, elementary functions. Did I upload it or not? I don't remember. I'll check it, and if I have not uploaded it, I'll upload it today. So elementary functions. So elementary functions, there are different types of elementary functions. We have polynomial function. Polynomial functions are like this. When I say functions, I am speaking about actually functions of complex variables. That means if z is a complex variable, fz, and that is a function, and there are different types. So polynomial function is like this, where w is equal to a naught z to the power n plus a1 z to the power n minus 1 plus, it goes like this, plus a n minus 1 z. You see the powers of z are decreasing like this, and plus a n like this. It's nothing but a polynomial. You see, it's like this. It may be a naught, may be some constant. So you see, what are this? A naught, where a naught, a1 up to a n are complex constants. Complex constants, and n is a positive integer. Is a positive integer, and what is n? N is a positive integer. It is also the degree of the polynomial, just as we had learned in algebra. So actually we are doing complex algebra here. And what do we mean by complex constants? See, otherwise if it would not have been complex constants, these numbers would have been maybe 2z to the power n plus 4z to the power n minus 1 plus dot 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 plus 5z. We may have this plus 3. We could have got like this. But when I say complex constants, it may be, so these things may be like this. Maybe 2 plus 3i, then I may have only 3i. In some, the real may not be there, the real part may not be there. So these